So, good evening to all distinguished participants, esteemed resource persons, and respected faculty members. It is with great enthusiasm that we welcome you to day two of AICT and ATL sponsored 6-day FDP on exploring emerging trends in communication systems integrated with quantum computing technologies, organized by Department of ECE, Ramchandra College of Engineering Autonomous, Eluru, from 18th to 23rd August 2025. Yesterday marked a powerful beginning filled with insightful sessions, vibrant discussions, and a shared curiosity about the future of communication systems and quantum computing. Today, we continue that momentum with resource person Dr. B.T. Krishna sir, Professor and Director, Institute of Science and Technology, JNTU-K, Kakinada. In spite of his busy schedule, sir has accepted our invitation to act as resource person for today's session 1 on quantum computing and applications in the perspective of electronics and communication engineering. Thank you, sir, for readily accepting our request, and it's pleasure to have you here for delivering session 1. Thank you,
Okay.
sir.
Thank you, madam.
As we analyze deeper into the convergence of classical communication frameworks with quantum technologies, we stand at the frontier of innovation. And the sessions ahead promise to illuminate cutting edge research, practical applications, and the pedagogical shifts needed to prepare the next generation of engineers and scientists. We are honored to host thought leaders and experts who will guide us through today's explorations. Your active participation, questions, and reflections are what make this program truly impactful. Let's embrace today with open minds and collaborative spirit. May it be a day of discovery, dialogue, and inspiration. Now, I invite Mrs. K. Jeevanjyoti ma'am to introduce today's session 1 resource person through profile reading. Ma'am, please.
Yes, ma'am. Good evening, respected dignitaries, colleagues, and guests. Myself, K. Jeevan Jyoti, Assistant Professor in EC Department. It gives me great honor and pleasure to introduce today's distinguished resource person, Professor Dr.B.T.Krishna, a renowned academician in the field of electronics and communication engineering. Dr. Krishna is a professor at Jawaharlal Nehru Technological University, Kakinada. He completed his BE, ME, and PhD from Andhra University, Visakhapatnam. His research areas include fractional order systems, signal processing, nanoelectronics, and analog VLSI with applications in underwater and biomedical systems. He has guided 13 PhD scholars and more than 30 MTech projects, contributing immensely to research and mentoring. With over 110 research publications, 11 Indian patents, and recognition in Marcus Who's Who in the world, his academic contributions are widely acknowledged. Dr. Krishna has received several honors, including the Best Teacher Award from JNTK in 2021 and the AP State Best Teacher Award in 2024. He has also participated in many international conferences, chaired sessions, and received Best Paper awards. He has successfully completed and secured major research projects from UGC, DST, and RUSA, and currently holds editorial responsibilities in reputed international journals. He has also served JNDK in key roles such as Head of the Department of ECE, Director of Industry Institute Interaction, and Director of Institute of Science and Technology. We are truly privileged to have him with us today. Please join me in welcoming Professor Battula Tirumala Krishna Garu. Thank you, sir. Thank you so much.
Thank you, ma'am. Now I invite Dr. B.T. Krishna sir to take over the session. Sir, please.
Hello, hello, madam.
Sir,
Okay, okay, okay. Thank you. Thanks for your welcome. Now, shall I can start the presentation, madam?
Excellent.
Huh?
Sure, sir. Sir, we can please.
Excellent. Sir,
Hello?
please proceed, sir.
Okay, 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 madam. So, thanks to the administration and management of Ramchandra College of Engineering, Eluru for giving me an opportunity to speak few words about quantum computing and applications in with respect to EC people. So I am B.T. Krishna, T.K. Batula from Jawaharlal Nehru Technological University, Kakinada. So this is the organization of the presentation. First, I wish to teach some of the historical evidences and what are the government initiatives that are taken to bring this technology into India and what are the mathematical techniques we have to know. Then I will explain you about what is qubit, what is quantum gate, how to do the quantum programming, what are the positives and negatives of the quantum computers, and what are the books that are suggested for further reading. And as far as the applications in electronics and communication engineering is concerned, I want to briefly explain about quantum signal processing, antennas applications, and quantum cellular automata based filter design. These are the points that are going to be discussed in today's class. So the first one is about the history. So basically, let us define what is a quantum computer. So from some of the textbooks, you have taken the definition as a quantum computer is a machine that performs calculations based on the laws of quantum mechanics. Many people will assume that without knowing quantum mechanics and physics, we cannot study quantum computing. This is difficult, but that is we should have a primary knowledge. In the first year itself, engineering itself, all of us will study double slit experiment in a dark room. That is necessary, that is sufficient. And at the same time, having a knowledge on the matrices and having a knowledge on the Python is more than sufficient. And at the same time, we need a knowledge on the basic gates in the digital electronics. Okay, these are the things we should we have knowledge to study about quantum computing. So the first person who has proposed this is nothing but Feynman in 1982. He has proposed a idea of creating machines based on the laws of quantum mechanics instead of the laws of classical physics. He is the first person in 1982. So accordingly, in 1985, David Juice developed the quantum Turing machine, showing that quantum circuits are universal. This is the first development in the year 1985. In 1994, Shar has developed an algorithm, which is the first quantum algorithm, to find the factors of a very large number. And then subsequently, Grover has developed an algorithm, is quantum search algorithm. The name of that algorithm is quantum search algorithm. It will have an order of root n complexity. Okay, so this diagram gives from the beginning to till today. In 1929, Dirac, we will study about Dirac function, delta of t, unit impulse function. That person, one of the founders of the uh, quantum physics, he writes that physicists now know all laws necessary to simulate chemical systems. He has given a notation which is useful in the quantum mechanics. Prior to him, in 1925, Schrodinger equation was proposed. We have studied this equation. Then in 1935, the EPR paradox is a thought experiment intended to demonstrate an inherent paradox. This EPR paradox has been proposed. In 1965, Feynman's theories of quantum electrodynamics has been proposed. In 1981, Feynman proposes quantum phenomena. I have already told you. In 1984, quantum cryptography was developed by IBM. In 1994, Shor's algorithm has been proposed. In 1996, Grover's algorithm, which is nothing but database algorithm, was proposed. In 1998, first working Q-qubit quantum computer is demonstrated. So here, the classical digital electronics, we will call it element as a bit. Here, in this quantum computer, we will call it as a qubit. I will explain you what is qubit. In the year 1998, first working 2-qubit quantum computer was demonstrated. In 2001, 7-qubit computer, researchers at IBM and Stanford factor the number 15. 7-qubit computer was proposed in 2001. In 2004 to 5, first photon and entanglement plus first quantum byte was qubit was proposed. In 2010, uh, D-Wave company announces first commercially available quantum computer in 2010. In 2016, IBM makes 5-qubit quantum computer available to developers and researchers for experimentation via its cloud portal. Nowadays also we have to make use of the same cloud portal. In January 2017, D-Wave makes 2000 Q system commercially available. In May 2017, IBM announces 16 qubit machine. In September 2017, Microsoft reveals quantum programming language. In 2017, quantum programming language was released by Microsoft. In the October 2017, Google announces Open Fermion, open source chemistry package for quantum computing. This is one of the applications even till today. Quantum computer finds application in chemistry. In November 2017, IBM announces 20 qubit machine. Okay. In 2018, Intel confirms development of 49 qubit chip. Chip has manufactured in the 2018. That means with the advancement of the VLSI technology, this is also possible. In 2019, Google claims to have reached quantum supremacy for the first time. And 2019, IBM launches first commercial 20 qubit quantum computer. Okay, so this is the technological development in the starting from 2020 as available from the internet. So how the quantum computer look like is a question. These are some of the pictures which shows a quantum computer. The first one is the Chinese 76 qubit photon based quantum computer. Second one is ion trap based 32 qubit quantum computer. And the third one is IBM 53 qubit superconductor based quantum computer. This is proposed by IBM. The third diagram, this diagram. Okay, these are the different appearances of the quantum computer. So next, nowadays everybody is talking about quantum computer, quantum computing and its applications. What government is doing? The Modi sir government has given 6,004 crores for the 8 academic years 2023 to 24 to 2030 to 31 to develop a quantum computer in India. As well as at the same time, it has opened one mission under direct Department of Science and Technology. The name of the mission is National Quantum Mission. The purpose of this mission is to bring the quantum technology to each and every person. That's why the craze has been suddenly came into account, and we are studying this. In the 8 years, we have to design a quantum computer with 52,000 physical qubits in various platforms like superconducting and photonic technology and so on and so forth. At the same time, the purpose of this NQM is to open T hubs, technology thematic hubs in these 4 areas. One is quantum computing, other one is quantum communication, and quantum sensing and metrology, quantum materials and devices. So surprisingly, all the 4 are related to electronics and communication engineering person. Quantum computing, whenever there is an algorithm, okay, definitely the role of the transform techniques comes into picture. Quantum computing is ours. Quantum communication, with the development of the photon, okay, photon based communication, okay, electronics and communication in the role is present. Sensors design, quantum sensing, okay, it is our job only. We will design our sister concern instrumentation people will work on the sensors design. Quantum materials and devices, quantum development, we used to develop so many devices to be fabricated. Whenever the situation of whenever the of fabrication comes, we have to think about the material, which is nothing but silicon, germanium, gallium arsenide, okay, only indium phosphate, only those materials only. So the role of electronics and communication engineering person in this area is 100% in my opinion. So this is the theory. IBM, that means thematic hubs has been opened in 4 institutes. Quantum computing hub has been opened in the IISc Bangalore. Quantum communication hub is present in IIT Madras in collaboration with CDOT New Delhi. Quantum sensing and metrology hub is present in IIT Bombay. Quantum materials and devices hub is present in IIT Delhi. At the same time, nowadays QT 00 to QT 12 or 13 FTPs which are online or conducted by the MNIT Jaipur. At present it is running from 18th it has started. Daily timings are 2 to 4. There are online FTPs to bring this technology to reach everyone. Okay, and there is an NPTEL course on quantum computing is also opened this semester only. And whenever you have written a small proposal on quantum computing, AICT is also sponsoring several of the Atal FDPs. And as far as our university is concerned, in R23 in third year, we have introduced this course, quantum computing course. For R25 regulations, that will be introduced in the first year itself. We have introduced this quantum computing in the curriculum. And Andhra University has started B.Tech quantum computing with 30 number of seats in EC department from this academic year, 2025 academic year. Madam, am I audible? Hello? Hello?
Yes, sir, audible.
Okay, thank you. So this is government of Andhra Pradesh on 30th June. It has started Quantum Valley near Amravati, and this is the quantum computer that has been exhibited by IBM quantum computer at the Amravati rally. Okay, so government of Andhra Pradesh has instruction to several universities to make that this technology will reach to each and every student or every user. Okay, so now this is the historical perspective and government initiations is over. Now we need to study this quantum computing. What are the prerequisite mathematics symbols? So these prerequisites includes the work by Professor Paul Dirac, who is from 1902 to 1984. He has introduced a notation. Okay, those notations are nothing but cat and bra. So here you see there is a less than symbol followed by psi, then there is a vertical line. That psi is optional. Any name you can put from A to Z, or any symbol you can put, alpha, beta, gamma, anything. Okay, that is optional. Whenever arrow is directed towards the left side, okay, less than arrow, that symbol is called as bra. Whenever it is directed towards the right side, that symbol is called as the ket. Okay, so bra will result a row vector and ket will result a column vector. So this is notation is nothing but a Dirac notation or bracket notation. A bra operator can work on a ket operator can work on a bra operator. Okay, so here you see, whenever I have placed a 0 in place of psi, I will get a row vector like this 1 0. Okay, and whenever I place a 1 in place of psi, I will get a row vector like this 0 1. Here you see there are 3 lines here. Okay, this one is ket 0 is equal to a matrix 1 0, ket 1 is equal to matrix 0 1. That means there are 3 lines. This is equal to by definition. That means this is equal to by definition, not equal to. Okay, so ket 0 is equal to 1 0, ket 1 is equal to 0 1, ket plus is 1 by root 2, 1 by 1 1, ket minus is equal to by definition 1 by root 2, 1 minus 1. Okay, so whenever I have written a bra minus 1, then that one will be equal to 1 by root 2, 1 minus 1 in the horizontal direction, not in the vertical direction. Okay, so these are some of the operations. Bra times ket returns a scalar. Okay, whenever I have done this operation on 2 variables, that will result a scalar. Whenever ket times bra, whenever I have done the operation ket times bra like this, when this has been multiplied together, I will get a matrix. Okay, so we have to study in detail in the textbooks, we can study, but this is the basic notation and basic elements we should know. And second one, we need to study this subject in a more to understand more clearly. We have to study about the tensor product. So okay, tensor product will have a x symbol embedded in a circle. It is not plus symbol, it is a into symbol, a multiplication symbol embedded in circle. So this multiplies 2 vectors to produce longer vector, or 2 matrices to produce a larger vector. Okay, so let us take an example of these 2 matrices A B, tensor product of CD. That means A should multiply with C first, then A should multiply with D next, then B should multiply with C first, then B should multiply with D next. Like this, this is an example he has given. 1, 2, 3, 4. 1 into 3, 1 into 4. 2 into 3, 2 into 4. I will get this matrix. Whenever this is applied between two matrices like this, okay, A should multiply this matrix first. That means AE, AF, AG, AH. Then I have to multiply with B, BE, BF, BG, BH. Then with C, CE, CF, CG, CH. With D, DE, DF, DG, DH. So this is the tensor product we should know. These two notations is useful in order to understand this subject. Okay, and at the same time we should have some knowledge on what is Hermitian matrix. Okay, what is the transpose of a matrix. Okay, what is the determinant of a matrix. All these things we should know, and at the same time we should know what is a complex number. All of you know that a complex number can be represented as a plus jb. Okay, b is nothing but the imaginary part, j is nothing but root minus 1. Okay, and that can be represented in the coordinate system. A complex number can be represented on a coordinate system. Okay, in our control system subject we will represent on x-axis as sigma, on y-axis as j omega. Any complex number can be represented. We have studied so much of complex numbers in Laplace transform, okay, Fourier transform. Okay, we know. So we know the representation zero diagrams also. We know what are the complex poles and complex zeros. Okay, all of us know. So matrices, okay, complex numbers, and that notation, brand ket notation is more than sufficient to study about this subject. And we need a knowledge on basic gates. Now let us define the fundamental component. Fundamental component in the quantum computers is nothing but the qubit. Okay, as all of you know, we have studied digital electronics. We have studied so many of the classical logic gates. Okay, we know what is AND operation, OR operation, exclusive OR operation, AND operation, OR operation. All of us know. There, bit is the fundamental concept. So the bit is the fundamental concept of classical computation. Okay, and whereas in quantum computation and quantum information, that is the fundamental concept is nothing but quantum bit or qubit. Then how to represent quantum bit or qubit? Quantum bit can be represented either as 0 or 1. In our digital electronics we will have only two states, 0 and 1. Okay, only two states. But in case of quantum computing we will have cat 0, cat 1, or any state, any other than these two. Okay, so that the fundamental difference between bits and qubits is that qubit can be either in state 0 or state 1. State 1, but in case of classical computation it should exist only in 0 state, or it should exist only in the 1 state. This is the difference. Okay, so two possible states for qubit are cat 0 and cat 1, which as you might guess corresponds to state 0 1 for classic bit. In general we will write, okay, this operator as like this: cat psi is equal to alpha times cat 0 plus beta times cat 1. Alpha and beta are constants, are complex numbers. Okay, but here the condition is square of alpha plus square of beta to be equal to 1. What is square? Why square has been used here? Alpha and beta indicates the quantum states. In quantum mechanics, square of a number will represent the probability. Okay, so here you see this is an interpolation operator. We are saying that a qubit can represent either 0 or 1. It can exist in any state. So we have written this as alpha. Beta should be 1 minus alpha, because some of these two, alpha and beta, should be 1 only as far as our classical mathematics is concerned. But here, whenever I have squared alpha, that represents probability of existing in 0th state. Whenever I have squared beta, that indicates that probability of existing in 1 state. So some of the two probability equal to 1 as far as our basic class of probability. Okay, this is the condition, and this is the representation of this operator. Okay, then there are two distinct states, cat 0 and cat 1. we know that a complex number can be represented in a coordinate system. Similarly, these qubits also can be represented, okay, on a circle, okay, that is named as 1 minute sir. That is named as block sphere. So here you see this is an example of block sphere. In the block sphere, cat 0 represents 0.001. It is north, and cat 1 is in the south pole. And x-axis comes out of the block sphere. Y-axis is y-axis represents to the side, and z-axis represents to the upper orientation up. So this is the representation, and this topmost value is cat 0, and bottommost value is nothing but the cat 1. Okay, now cat 0 represents xyz point as 0, 0, 1, and cat 1 represents xyz points as 0, 0, minus 1. So qubit can be anywhere in this sphere. So to understand here, I have taken from one article how to represent. Cat 0 is nothing but 1, 0, that is on the topmost, and cat 1 is bottommost one, okay, 0, 1. So plus and minus, these are nothing but the orthogonal x basis stages, plus and minus in the x direction. And similarly, plus I and minus r, they are nothing but the orthogonal basis in the y direction. This we will study orthogonal basis in communication system Taub and Schilling second chapter. That chapter is very useful for the people who wants to work in the quantum computing, second chapter, okay, for Taub and Schilling principles of communication systems. Okay, so plus is cat plus is nothing but 1 by root 2 times 1, 1. Cat minus is nothing but 1 by root 2 times 1 minus 1. Cat plus I is equal to 1 by root 2 times 1 j. J is nothing but root minus 1. Cat minus, you should not confuse with this minus I and this minus j. They are different. This means this plus, and cat minus I is 1 by root 2 1 minus j, which is located on the leftmost part. Cat plus I is located on the rightmost y-axis. Cat 1 is located in the bottom, cat 0 is located. Other values will be rotated here, anywhere in this circle. Okay, in general, alpha and beta, they are going to be written as cos theta by 2, and beta is nothing but e power j phi sin theta by 2, where phi is nothing but this angle as represented in the diagram. This is the block sphere. Any value, okay, should fall in this sphere only in quantum computation. Okay, so we have told you about the qubits, and we know that in quantum computation, qubit can be anywhere between cat 0 and cat 1. Okay, any value. So these qubits will have some properties. They are nothing which are useful, which we have studied in the first year of engineering. Okay, we doesn't know that we have studied them. Okay, so those properties are superposition property, entanglement property, coherence property, decoherence property. So what is superposition? All of you know superposition is nothing but uh, existing in different places at the same time. So we have studied this in superposition and entanglement, coherence and decoherence in Young's double slit experiment in dark room. We will in physics lab, we will go to the dark room. Okay, this was invented by Young's scientist Young's in 1801. So the main property of quantum bits, which is responsible for the exponential power of quantum computer, is superposition. That means because of the superposition property only, this is the speed of operation of execution of any algorithm has been increased exponentially as compared to classical computation. So this property defines that in quantum sized world, the particles can be present in two places at the same time, which is impossible and irrelevant in the macroscopic classical world. That means a particle can be present in two places at the same time, but whereas in our classical computation, it should be at only one place. Entanglement. Entanglement is a phenomenon in quantum mechanics where two or more particles become correlated in such a way that the state of one particle cannot be described independently of the state of the other particle. So this is entanglement. Okay, there is a correlation between the two number of particles. Coherence is as the quantum states in the qubits acts as wave. The two or more quantum state waveforms having an equal phase and frequency will add up, resulting in the formation of waveform, which is a combination of two states, and these two waveforms are said to be in coherence. So there is a relationship between these definitions, superposition, coherence, with the Fourier series. All of you know that in Fourier series, any signal can be represented as a DC term and as well as a combination of sinusoidal and cosinusoidal components. While explaining about the amplifiers, every teacher used to explain that if all the individual components has been equally amplified in both the amplitude as well as the phase angle, then only you will not get any distortion. You see here, the quantum state waveforms having an equal phase and frequency will add up, resulting in the formation of waveform, which is a combination of two states. Just assume this definition, then correlate this definition with the definition of the Fourier series. We will better, that is what is meant by coherence. Decoherence is decoherence is when there is a phase shift of 180 degrees, the result will become equal to 0, and you will have dark lights. Dark, you have seen the in the dark room, we have seen both white and dark fringes while doing the Newton rings or some experiments, as remember. Okay, so decoherence means having a phase shift of 180 degrees between the two frequency signals. Okay, so these are some of the properties. These properties has been used in the design of communication system, in the design of the antennas, in the design of Fourier transform, in the design of any quantum algorithm. Okay, now let us see the comparison of the bits and quantum bits. As far as the classical bits is concerned, it can be in two distinct states, 0 and 1. Whereas the quantum bit is concerned, it can be in state ket 0 or in state ket 1 or any other state, that is a linear combination of the two states. We have written that ket is equal to alpha ket 0 plus beta ket 1. Okay, so any state is possible. That's why there is a possibility of exponential rise in the competition. Can be measured completely, classical bits. Okay, can be measured partially with given probability, are not changed by measurement. Classical bits are not changed, but these quantum bits are going to be changed. Can be copied, classical bits, but quantum bit information cannot be copied. Can be erased, classical bit can be erased, but it cannot be erased. These are the two distinct advantages. They cannot be copied, they cannot be erased. Okay, so these are the comparisons of qubits. Now this is the introduction. So since we need a circuit. Okay, we are already having some circuits which can process logic 1 and logic 0. We have studied it as a switching theory logic design, digital electronics, so on and so forth. But what about the circuits which will operate on ket 0 and ket 1? Okay, they are nothing but the quantum gates. We have studied their logic gates, AND gate, OR gate, exclusive OR, but we are here also we are having logic gates which can operate on this data. Okay, ket 0 and ket 1 are a linear combination of these. But here one important property you have to remember, that the number of inputs and number of outputs should be same, and these quantum gates are reversible always. But whereas the classical logic gates, they are not reversible. Okay, so and at the same time every gate operation you has to be unitary. Okay, so quantum gate is a basic quantum circuit operating on the qubits. And let us see some of the quantum gates and classical gates to understand the here quantum gates also will have the truth table, whereas our classical gates also will have truth table. Okay, so these are the famous operators and gates and their symbols. See, poly X gate is going to be represented as X and its matrix is 0 1 1 0. Poly Y gate is going to be represented as a square box filled with Y, 0 minus I 0. Poly Z gate is nothing but 1 0 0 minus 1. Hadamard gate is 1 by root 2 1 1 1 minus 1. Phase SP is 1 0 0 I. Pi by 8 gate T gate is 1 0 0 E pi by 4. C naught gate is going to be represented like this: 1 1 0 0 0 and 0 1 0 0 So we can study this in vertical direction or in a horizontal direction. Okay, you see this follows this Carnage map principle. Okay, control jet gate is like this, and swapping of gate is also possible. Information can be swapped in the quantum gates. uh, this is the matrix 1000001001000001 and Toffoli gate. Okay, this one. So it is surprising that every one of you might have worked on these gates. You have written a Verila code in your BTech project. Reversible gates. I have listened several times while attending BTech projects and MTech projects. Okay, they are useful in the competition. Okay, and these are the classic gates, as all of you: NOT gate, AND gate, and AND gate, OR gate, NOR gate, XOR gate, XNOR gate, and so on and so forth. So why this slide is very important, because every student who is listening should know how to program these quantum gates, because in quantum competition you will get gates only. You have if you have written a Verila code, and if you have converted into RTL schema, you will get a diagram in terms of AND gates, OR gates, like this. But if you have written a Python code, you will get a diagram in terms of these gates. Okay, so here you see, this is the classical digital circuit. Here this can process bits. Here there is a OR gate, a NOT gate, AND gates, and so on and so forth. Here you see there is a T gate, S gate, Hadamard gate, H gate, Toffoli gate, and there are interconnections. This is the qubit representation. So many books are available to produce such type of circuits by writing the Python code. Whenever I have taken a function, okay, a SOP form or a POS form, okay, if I have written the code, okay, using Python, I should get such type of signal, such type of diagram. Okay, so this is the job of every electronics and communication engineering student, to produce such diagrams, okay, by programming in some languages. Okay, I will tell you. Next question is, you may ask a question: how to program? What is quantum programming? Okay, so in order to write the code in this in order to write code, there are several programming languages are they have been adapted for quantum computing. Okay, so the purpose of quantum programming languages is to provide a tool for researchers, not a tool for programmers on it. Quantum computation language is an example of such language. And similarly, IBM has developed quantum information science kit. Okay, quantum computational language. These are two examples of quantum programming. Okay, so Qiskit is an open source framework for quantum computing. It is available freely. It provides tools for creating and manipulating quantum programs and running them on prototype quantum devices on quantum experience or cloud-based access. This cloud-based access we have to procure. We have to pay some money to the IBM company. Now government is providing this. I think somebody has told they will provide free access to use to do this computation using our quantum computer. But we should know how to program. But the basic programming language, okay, is nothing but Python or some other programming languages. In the next slide, I have gathered the information from, you see some of the programming languages. CARP is a programming language which is useful for creating, editing, and invoking noisy intermediate scale quantum circuits. The main programming language is Python. This runs in Windows, Mac, and Linux. Cliff Odds.jl, efficient calculation of Clifford circuit in Julia, and this runs with the programming language Julia, and licenses for MIT and Windows, Mac, Linux are the operating systems. Demode, similarly D-Wave system. Okay, this is based on the Python language, runs only on Linux and Mac, operator system dependent. Okay, similarly, Fermilib runs only on Windows, Mac, and Linux, and Open Formion. Okay, this runs on Python, Windows, Mac, and Linux, And Project Q, this is open source software framework for quantum computing, C++ and Python, and this runs with Windows, Mac, and Linux. So these are the different programming languages. And Qiskit tutorials, Qiskit Terra and Aqua, quantum information science kit for writing experiments, programs, and applications, runs with Windows, Mac, and Linux. Qiskit tutorials, collection of Jupyter notebooks using Qiskit. All of you know what is Jupyter, what is Anaconda. Okay, Python is the programming language, is suitable to run on Windows, Mac, and Linux. And kinkit.js, quantum information science kit for JavaScript. This runs with Windows, Mac, and Linux. QRack and Quantum Fog, Quantum Plus Plus, Qbiter, Quirk, Reference QEM, SCAF CC, Strawberry Fields, XACC, XACC VQE. These are, you see, almost all programs runs with on Windows, Mac, and Linux. Many of them are the open source programming languages. Okay, the famous one is Qiskit, and there are so many books available uh, on Qiskit in the internet. You can find, so you can learn it easily, which is a Python based one. So these are some of the quantum programming languages. Okay, so now let us see what is the we came to know that quantum computers are offering with large speed. Okay, the computations are done with large speed compared to the classical computers. Okay, that is because of the four properties. Now let us see what are the problems with quantum computers. So there is decoherence. That means quantum system is extremely sensitive to external environment, so it should be safely isolated. Okay, so because of this property, uh, uh, these are extremely sensitive to noise, so it should be um, sorry, so these quantum computers are extremely sensitive to noise. It is hard to achieve the decoherence time that is more than algorithm running time. And at the same time, physical implementation of the computations is difficult. But as a student, electronics and communication engineering student, let us suppose there is an algorithm, Fourier transform or quantum Fourier transform, people nowadays calling quantum neural network, they are calling. Okay, quantum particle sum optimization. Okay, so they should be implemented in the hardware form, because since it is not an ordinary computer as available today just like a desktop. Okay, we have to pay some money to use its services. It is better for us to go for the duplicate. That means whenever quantum Fourier transform is there, we are having FPGA, we are having field programmable gate array, or microcontroller, or a DSP processor. We are having field programmable analog array. We have to invent a duplicate circuit which can perform the operation. The quantum Fourier transform can be simulated using, or can be executed using a FPGA kit. Okay, that is nothing but the practical implementation. Okay, any student can do to avoid this limitation. Okay, so, and at the same time, the available quantum algorithms cannot solve all the problems that are existing in each and every field of science and engineering. Okay, so we have to develop new quantum algorithms. That's why quantum algorithms projects has been innovated till 18th of this month by Department of Science and Technology. Okay, new quantum algorithms to solve the more problems. This is one of the limitations. And at the same time, if the program running time increases with the exponentially with the matrix size. Okay, so these are some of the pros and cons that are present with quantum computers. So the what about further reading? Okay, so these are some of the textbooks which will illustrate us in a clear manner quantum computing for everyone, Chris Bernhardt, and quantum computing in practice with Qiskit and IBM quantum experience. Okay, practical research for quantum computer coding at the gate and algorithm level with Python, Hessi Norian, and Jack D. Hidari, quantum computing, an applied approach by the Springer publisher. Okay, so you can download, they are available. Okay, you can download, and you can go through the more details. Okay, so these are the suggestions for further reading by the student. Next, next part, the first part is the fundamentals part. Everybody should explain this. Every teacher, whether he is a physics teacher, mathematics teacher, okay, electronics and communication, electronics and electrical engineering, computer science, everybody. Okay, now there are some algorithms I want to bring to your notice. Everybody should know quantum search algorithm. We should know what is Schwarz algorithm. We should know Grover's algorithm. Okay, I am not touching all these algorithms. You should know how to program those algorithms also, and you have to bring them into your application. Okay, so first, let us see some of the possible applications of the quantum competition, quantum computer in our electronics and communication engineering. There are several applications, sir, but I have concentrated only mainly on the third one, quantum cellular automata based digital filter design. And up to some extent I can explain about quantum signal processing. And I have seen in the brochure there are several teachers who will teach you about quantum antennas, but I will tell what are the advantages and disadvantages of this quantum antennas. What is the difference between classical antenna and quantum antenna? So first let us see, so this is taken from one of the journal paper. These are some of the applications of quantum computing. Quantum computing is finding application in the cryptography. Quantum cryptography has been developed in cyber security. It is finding several applications nowadays. It is a more hot topic, cyber security and quantum computing. Okay, next, financial modeling. Financial modeling, this the check is not there. While I was writing latex code, I have written check. Okay, and it is finding applications in weather forecasting. It is finding applications in the drug design in the field of pharmacy. Okay, so these are some of the applications. Very few I have mentioned here. There are several applications nowadays. Classical computing is going to be replaced with quantum computing. Okay, several people has invented more powerful algorithms towards the optimization techniques, towards the machine learning. Quantum machine learning is also possible. Quantum cryptography, cyber security, finance, and these are some of the applications. So first, without knowing that we are working on quantum computer, in 2023 one student has worked on digital filter implementation using quantum dot cellular automata in under my guidance. First I will explain that, then I will come to quantum signal processing. Give me permission to go to this slide. Easy here. So our work is quantum cellular automata based digital filter design. So we will concentrate mainly on the design of differentiators and integrators. This is the work we carried out in from 2006 onwards. So a digital differentiator is to find the time derivative of the incoming signal. It finds applications in radar. It finds applications in biomedical engineering. It finds applications in sonars. Okay, all real-time applications. Okay, we'll need the design of the digital differentiators. So digital differentiator is simply in the analog sense, it is s Laplace transform variable s. Dy by dt will have a Laplace transform of s. In the frequency domain, j omega, where j is nothing but root minus 1. So all of you know that digital filter can be two types. One is FR type, and other one is the IR type, finite impulse response, infinite impulse response type. So infinite impulse response type filters are preferred because of the less circuit complexity and less order. That means for real-time applications, there the delay should be as less as possible, and the phase matching should be present, and order should be as less as possible. So this is the IAR. So IAR type differentiators we have concentrated in our lab. Okay, IAR lab. So these are the existing digital differentiators. Z minus 1 by T, Z, 2 by T, Z minus 1 by Z plus 1. All of you know that this is a bilinear transformation. and these are other second order digital differentiators, third order digital differentiators. We have done an implementation of this 2 by t z minus 1 by z plus 1 using quantum dot cellular automata. So what these are the magnitude and phase responses we have compared. This is possible with MATLAB. Let us leave it. So now let us see what is meant by quantum dot cellular automata. So quantum dot cellular automata, it is a technique which was proposed by Craig Lent, a professor of electrical engineering at the University of Notre Dame. Because of the recent development in nanotechnology, this QCA is finding its attention. Okay, so this the idea of employing cellular automata architectures which compatible with nanometer scale quantum devices, which is called as the quantum cellular automata. So this quantum cellular automata works on the electron spin. Okay, uh, based on that only values will be assigned. So uh, here let us see this one. So quantum dot cellular automata cells, these are the basic cells. When this black dots indicates electron occupation and white dots indicates there is no presence of an electron. Okay, so this is the first one will represent a value of +1 basic cell with polarization, and the second one will represent a value of -1 whenever they are present in this direction. Similarly, these cells can be created using a software QCA designer, which is a free software, quantum cellular automata designer. Okay, so this cell is 18 by 18 nanometer by 18 nanometer 4 dot cell. Okay, this will have 4 quantum dots, which is called as the quantum dots. Okay, so this is first one is the normal cell, second one is the rotated cell, third one is the vertical cell, crossover cell, fixed polarized cell. That means depending upon requirements we have to make use of any one of these 5 cells. Okay, so next one is this is a crossover. That means by using the wires, both coplanar crossing and multi-layer crossing can be done. So for the single layer or coplanar crossover, the crossing is implemented using both 90 degrees and 45 degrees QCA cells. The first one is 90 degree horizontal one is 90 degrees square, and second one is nothing but the 45 degrees square. Okay, for multi-layer crossing, the crossing is achieved by multi-layer placement of QCA cells. Both the normals and rotated cells can be using this one. Second diagram is the multi-layer crossover. Cells can be placed in like this uh, in the software. Vertical cells are used to do the crossover. Okay, so QCA designer, it is a free software, and the simulation tool for quantum dot cellular automata is QCA designer. QCA designer is developed at a TIPS laboratory by Conrad Wallace, University of Calgary, Canada, which is an open source one. So here there are clocking. There are 4 clocks. Okay, 4 places of the clock. In the first phase there is a switching mode. Second one is the hold mode, and third one is the release mode, and fourth one is nothing but the relax mode. Okay, so these are the corresponding diagrams of the cells. Okay, so now what we have done is we have first simulated an inverter. Okay, using QCA inverter. This is the circuit diagram of the inverter. Cells has to be arranged like this. This is the input and this is inverted output. Okay, so this is the clock signal I have given. Okay, these are input and output waveforms. Next one is important one is the majority gate. The function for majority gate is AB plus BC plus CA, and this is the truth table. And this is the diagram corresponding to 3 input majority gate, and these are the corresponding input and output waveforms generated by the QCA designer software. And third one is the important one is nothing but the delay element. Why we need delay element is in our transfer function there is a presence of z minus 1. Okay, in a digital transfer function there is a presence of z minus 1, so we need a delay element. The delay element has to be realized. So this is the circuit diagram of in terms of quantum cells, Okay, these are the QCA cells. Input is given here at the yellow side and output is taken at the this place. Okay, these are the corresponding input and output circuits. Okay, so now we have designed a full subtractor first. So this is the majority logic gate with three majority logic gates and two inverters has been used, and this will work in similar way as that of our full subtractor. Okay, and this is the corresponding input and output waveforms we have simulated and we have verified them. Okay, similar, this is the full subtractor which appears like this. Okay, full subtractor. So this is the corresponding input and output waveforms. Okay, similarly the same full subtractor can be realized using 3 input XOR gate. This is XOR. Okay, this is difference value and borrow value. Okay, and but here the complexity has been increased. Okay, so we have used the previous one. Now what we have done is, this is the circuit diagram which is simulated in the QC designer software to do the bilinear transformation action 2 by t z minus 1 by z plus 1. Okay, this is the first order digital differentiator. A digital circuit, a DSP circuit 2 by t z minus 1 by z plus 1 has been implemented using quantum cellular automata in our place. So we have sent this, since student has to go within a time, so we have sent to an IEEE conference and we have published, and these are the corresponding input and output waveforms. So if any of you are interested, this is also this falls under quantum computing only. In quantum computing textbooks, I have seen this QCA software and its uses. Several people has done a RAM design, several people has done a ALU design, several people has done a full adder, half adder. Okay, using quantum cellular automata. This is free of cost. The QC designer software you have to download. There will be user manual. Student has to learn. And this now people, there is no specific element is needed for the realization, hardware realization of quantum computer. Different companies, IBM, Oracle, they are trying in their own way. Somebody is using photon, somebody using other technique to realize the quantum computer. This may give them a solution, in my opinion. Okay, so the realization of electron spins is the only problem. You can simulate this quantum, this one. This is the digital signal processing circuit has been simulated, okay, by us 2 by t z minus 1. We are trying to simulate more in the in the coming sessions. Okay, so different using full subtractor we have done, and this experiment also we have done, and a 4-bit central difference, that means x of n minus x of n minus 1 by 2, that is nothing but the central differentiator. That experiment is also done by us. We have realized 3 digital differentiators, bilinear transformation, 1 minus z power minus 1 by 2 we have done. Okay, so these are the this is one of the application. Anybody can work in this. Okay, okay, so this is the bilinear transformation circuit. Okay, and this complex drawing of this complex diagram has not attracted many students. So students, some students has said, sir, we cannot do. So you see, this is the QCA designer software, freely downloadable. But one student has done this experiment, and we got theoretical values and experimental values matched with each other. Okay, the values that we have, we will take, we can take a real-time signal, ECG signal. You can take, you can differentiate it, or you can take a radar data, okay, or sonar data from NSTL or any some place, and you can give those inputs, okay, here, and you can check the whether there is a similarity between practical values and the experimental values also. Okay, so these are the, this is one of the possible applications an electronics and communication engineering student can do. Okay, here you see the input and output cells are not in the same clock zones, and also from the input and there is a crossover cells to avoid the disturbances, and hence all the delays are considered there. The output is 1.5 to 3 times delay from the input. The area has been reduced, okay, as far as our approach is concerned, and simulation speed is also increased as the number of cells are reduced as compared to both the circuits. These are some of the references we have taken in 2023, and we are continuing this year. Okay, this is one application. That means this is the equation we have simulated: bilinear transformation 2 by t z minus 1 by z plus 1. In order to simulate this DSP transfer function, first I have to write the difference equation. Okay, so the difference equation we have written like this: 2 into x of n minus x of n minus 1 is equal to y of n plus y of n minus 1. So this has to be from this I have to write an expression for the output signal. Y of n is equal to 2 into x of n minus x of n minus 1 minus y of n minus 1. There is a printing error is here. 2 into x of n minus x of n minus 1 minus y of n minus 1. This circuit, okay, this equation, this mathematical equation has been realized as like this. Okay, this is the circuit which performs that mathematical operation, and input and output signals are also has been verified by us in the QC using the QCA designer software. If any of the listeners they are interested, you can take a FIR filter or IIR filter, low pass, high pass. All these can be represented using the electron spin. Okay, so if there is any vacancy, you can try. I think it may not be present, but you can go to the design of some RAM design. You can take arithmetic logic unit design. So that type of problems, whatever you are doing with Verilog nowadays, people they are working in VLSA, in digital VLSA, what they are working, they can do with this QCA designer. Here, the advantage is this is a nanometer technology. Surprisingly, some of the softwares cannot offer the simulation for nano one. We have to buy with lakhs of rupees, but with a simple free open software, by learning the rotation, okay, and the different orientations of the electrons in the cells, okay, we can arrange them side by side, we can interconnect them, okay, and a student can do such type of exercise, or a PhD student also can work, because there are several papers are present in the application. So in these applications, okay, so this is one of the probable area in which a purely electronic student only can understand these concepts of QCA designer, okay, digital signal processing operations, okay, nano electronics. Okay, so this is the first area I wish to bring, because I can explain. I have explained. The second one is quantum signal processing. So all of you know that A to D, D to A converters are going to present in the classical signal processing, and there will be a block diagram. All of us will study the block diagram in digital signal processing subject. Okay, and we know what is meant by processing. So uh, here in one of the IEEE paper, one person has proposed a mixture of quantum signal processing and classical signal processing, and he has given a workflow diagram. This is the quantum signal processing workflow. There will be input signal, there will be classical pre-processing unit, then quantum signal processing, it is a must and should. Classical signal pre-processing is a optional one. Similarly, classical post-processing is an optional one, and that will be followed by an output signal. Okay, this is the quantum signal processing workflow. So here in the quantum signal processing, the process begins with the input signal, which may include raw data such as audio signal, image processing, image signal, array frequency signals. Optional classical pre-processing methods like signal conditioning or noise reduction can be applied depending on the system's requirement, although quantum algorithms often handle such tasks directly. So whatever the operations that we will do in the classical signal processing, all such operations can also be done in the quantum signal processing. but that field is not fully developed. Okay, as a compromise, what we are doing is we are using a combination of classical processing as well as the quantum signal processing in along with quantum signal processing unit. Okay, at the core, there lies a signal processing unit, which is a quantum signal processing unit employing advanced quantum algorithms such as quantum Fourier transform, okay, quantum phase estimation algorithm. This is used for phase detection and synchronization, and quantum filters for efficient noise reduction. So here you see there are some research areas. Quantum Fourier transform. So you know what is discrete Fourier transform. Okay, you know what is fast Fourier transform. You know Cooley 2K algorithm. Okay, you know decimation in time, decimation in frequency. So you can work on such developing such algorithm for the calculation of the quantum Fourier transform also. Okay, that you can take an access because that field is completely vacant. Okay, only quantum Fourier transform is defined. So no such algorithms has been done. Okay, I have gone through some textbooks. So any student can take this as a research problem. Okay, quantum phase estimation algorithm for phase detection and synchronization. Okay, they just like digital filters, designing of quantum filters for the noise reduction. Okay, such type of problems can be taken by anyone. So these quantum methods leverage parallelism to outperform classical counterparts. Optionally, classical post-processing techniques like error correction, result interpretation, or system integration may follow to refine the quantum output. The final output signal, whether filtered, transformed, or otherwise processed, is then ready for use in applications like quantum communication systems, control systems, or real-time analysis. The output of this workflow. This hybrid quantum classical approach demonstrates the potential for significant speed and accuracy improvements in signal processing tasks. And these are the advantages of the quantum signal processing. Quantum algorithms improve the signal processing efficiency. The quantum Fourier transform, quantum phase estimation algorithms provided notable improvements in speed and accuracy compared to classical signal processing methods. Okay, in here you see quantum Fourier transform demonstrated exponential speed up in frequency analysis tasks, particularly in processing high dimensional data such as image and audio signals. Quantum phase estimation has outperformed classical phase estimation techniques by offering higher precision in less time, making it ideal for applications in communication systems requiring real time signal synchronization. Okay, so this is the first advantage. Here the processing time has been okay reduced, but the speed of operation has been increased. Okay, whenever these techniques has been used in applications such as image processing and audio processing. Next, hybrid quantum classical approach is effective one. So due to current limitations in quantum hardware, hybrid approach combining quantum and classical systems proved to be the most practical solution. This is the solution to implement them. This approach resulted in faster processing times and enhanced accuracy, showing a pathway to integrate quantum techniques into existing signal processing systems without overhauling classical infrastructures, without affecting in a negative manner. The same infrastructure can be used by colliding, by collaborating both the classical technique and quantum techniques to produce to have hybrid quantum classical approach, okay, which is an effective one. Quantum machine learning enhances signal processing. This is third. Here people have invented quantum support vector machine has been invented, quantum neural network. Okay, so they have showed significant promise in tasks like noise filtering, feature extraction, and anomaly detection. Okay, so these algorithms performed faster training and exhibited better generalization for high dimensional data sets, leading to improved accuracy in real time signal processing applications like radar systems and IoT networks. I think these quantum machine learning algorithms may solve the problem of big data also. Okay, big data also. Okay, next, uh, now the only disadvantage is hardware. There is no such hardware implementation of these okay, till now, which is a big one. You have seen a quantum computer. We have to make it just like this desktop computer. In future, one may invent techniques, and suitable materials also has to be invented. So that's why I told you, EC student can work on quantum materials. Which material is suitable for producing hardware, okay, for quantum operations. Despite the promising results, current quantum hardware limitations such as qubit decoherence, noise, and connectivity hindered the scalability of the quantum algorithms. This is the disadvantage. We think in these few years, okay, people will invent this one also. How to eliminate such problems? Okay, so practical integrating. Okay, so this is integrating quantum computing into triple systems presents obstacles. Specialized quantum programming languages are needed for signal processing techniques, and compatibility with the classic systems is still a challenge. Okay, so ప్రస్తుతానికి సారీ at present a hybrid quantum classical model is most practical answer. Common framework for integration are essential for future general acceptance. Okay, so next, what are the quantum limitations of the quantum signal processing? Quantum hardware constraints. One of the primary limitations of the study is quantum state of current state of quantum hardware. Okay, next, limited availability of quantum processing power. Although quantum computing shows great potential for specific signal processing tasks, the availability of quantum processors capable of handling complex real-time applications is still needed. This is under research. Okay, so we have to work, the next generation has to work for producing such to eliminate such problems. Complexity of hardware systems. While hybrid quantum classical systems offer a viable solution in the short term, the integration of quantum algorithms with classical systems introduces complexity in terms of system architecture, programming, and real-time coordination. Okay, so the integration of these quantum algorithms and classical algorithms, okay, needs a separate system architecture. Okay, needs a programming. This also to be addressed. Okay, software and tooling limitations. The lack of dedicated quantum signal processing software and programming languages hampers the widespread use of quantum computing in signal processing applications. While platforms like Qiskit and CARK I have shown you, okay, provide quantum computing frameworks, they are primarily geared towards general purpose quantum algorithms rather than special signal processing tasks, limiting their utility for practitioners in the field. Okay, Python will solve the problem, but it is for general purpose algorithms only. That means finding the factorial, or generating a quantum gate, generating a quantum quantum circuit. Okay, like, but whenever specific signal processing, specific image processing, speech processing, okay, all these techniques are present. Okay, this is having its own limitations. Okay, next, data and algorithm constraints. While quantum algorithms such as quantum Fourier transform and quantum phase estimation demonstrate significant improvements in the specific signal processing task, their application to large data set and more complex problems still faces limitations. Okay, there is certain limitations, okay, in the data also. Okay, so this is about quantum signal processing. So because the next one is design of quantum antennas is also possible.